So the next piece, we've covered direct proportionality. Kind of the opposite of a direct proportionate is inverse proportionality. And inverse proportionalities are a function with a rational relationship between x and y. Okay? Rational refers to fractions. So we're going to be talking all about fractions here. Okay? And kind of switching around to viewing these as fractions. So inverse refers to fractions and whole numbers being flipped. This means that as one variable increases, the other variable decreases, okay? So these are all about our functions where as we move along the x-axis, we decrease our y-axis. So we start out high and we go low, okay? So make sure you get that vocab, okay? Inverse proportional relationships use the same symbol. We use the same proportionality symbol. Oh goodness, what am I doing? We use the same symbol, okay? The kind of half of a infinity sign thing, okay? And my tech is not doing what I want it to do, so we're gonna piece this together. All inverse proportional relationships are represented by one of these two things. They are the same thing, okay? If this fraction looking like this is confusing you, I will hand write out, it looks like y is equal to a 1 over x, or, y is equal to a over x, because we know that anytime we multiply a constant by a 1 in the numerator, that's the same as it going on the top. Okay, I don't know why we have A. These should be K's. I'm sorry, folks. But A over X, okay, or K over X, all right? So that, again, is our constant. So our constants now are like a fraction where X is now not being multiplied by our constant, but it's our constant divided by X. One of the key things with inverse proportional graphs is that they never cross the axes. So if you draw an inverse proportional graph, they will get really, really close to the y-axis, but they never actually hit it. Okay, and that is because if we have a 0 for x, and I plug that in my equation, y is equal to a, let's use 9 because that looks like a 9, over 0. 9 over 0, okay? If you type that in your calculator, it will say error because we cannot divide by an x, or by a 0, okay? So we will never cross the axes. Some examples, or an example for you, okay? Here I have a graph, and I'm going to graph an inverse proportional y is equal to, let's do 4 over x, okay? So if I put in a 1 for x, well then I have y is equal to 4 over 1, which is equal to 4. Okay, if I put in a 3, y is equal to 4 over 3. That's going to give me a decimal that I don't really want to graph, so I'm going to skip that one, okay? If I put in 2, y is equal to 4 divided by 2. Ooh, that's nice and easy. That's going to give us 2. If I put in, I don't know why I went from 3 to 2. If I put in 4, y is equal to 4 over 4, I get 1. And let's get wild and crazy and do 4 over 8. That is equal to a half, or 0.5. So I have 4 and 1, 8 and 0.5. So let's plot some of these points. 1, 4, 2, 2, 4, 1, 8, 1/2. Okay. And if I very carefully draw this line through there, you will see that it makes this nice arc shape. One of the really cool, there's a lot of really cool things that we can notice about inverse graphs, and I think they're super interesting. But if we take a look at some of these points here, you will notice, oops, this is not 4, 1, it is 1, 4. That at some point along the way, wherever we have an x, y, we're going to get a switched around version being yx. So here my x and my y's switched around, okay? Which means that there's also a point over here, and I didn't graph it super well, that would be, oh, that's not going to work, 0.58. So these switch around. The other really cool thing that we can notice is that if you multiply your x times your y, you will get your constant. That is a key fact of inverses. X times y gives you the constant, okay? So that is how you know something is an inverse proportion, is that anytime you multiply an x times a y, you will get your constant. 1 times 4 equals 4. 2 times 2 equals 4. 4 times 1 equals 4. 8 times a half equals 4. A half times 8 equals 4. Okay, so really cool properties of inverses. All right, some examples of where we see inverse proportionality, there's lots of them. It's a very common phenomenon in math, in science, in our world around us. Would be something like people eating and the time food lasts. So when we hear things about rationing, if you know what rationing is, that kind of has that word rationing, that word ratio in it, meaning a fraction. Okay, so rationing really comes from the idea that you are splitting things into groups like a fraction does. It splits it into groups and says, how long will this last? If I have a whole crate of apples and I have to eat them myself, it's going to take me a long time. If I have 20 people eating these apples, then it's not going to last as long. So that's a common example. Another common example is an area of a plot and sections of a plot. So if you think about a garden or folding a piece of paper, the more sections you have, the less size or area each plot is, okay? And lastly, another really common one is the number of people working and time to finish a task. They say many hands make light work. The more people working, the less time it will take. Finally, I have an example that kind of is a relationship of those. It says when a fleet has 60 people, the food lasts for 3 days. What is the relationship between the number of people and how long the food lasts? How many people can the ship have if the food needs to last for 20 days? So I'm going to break down these pieces. I'm going to look for my x, my y, and my constant value, okay? It says, when the fleet has 60 people, the food lasts for 3 days. What I like about this first sentence is that it tells me the relationship. It tells me that when I have 60 people, it's lasting for 3 days. So I have both a dependent and an independent variable. It sounds like the number of days is what's going to change depending on how many people we put on board. So the number of people is what we control or are independent, and it happens to be 60 people. The number of days is what changes, and it looks like we have 3 days. We don't know what our constant is, so that's what we're going to figure out. So I'm going to plug in my x and y to my proportion statement that says y is proportional when we have k over x. Well, let's plug in. It says that y is proportional, not y. What is our y value? 3 is proportional to 60 by some factor of k. If I want to get k by itself, I got to undo this fraction. So I am going to rewrite without the proportional sign so I can solve. and I'm going to multiply by the denominator on both sides. 3 times 60 gives me 180. If I multiply by the denominator, that's the same as saying 60k over 60. Anytime you have a number divided by itself, it equals 1. So I have 1k, or just k. So k is over here at 180. So my constant is 180. That is our key number that tells us how the number of days the food lasts and the number of people on the fleet of the cruise ship are related. So now I want to figure out how many people can the ship have if the food needs to last for 20 days. So 20 days is my new y value. And I'm going to use my k value. So I know that y is proportional when we have 180 over x. Using my k value. That's my proportionality statement. Okay. And so I'm going to plug in the y that I know. So I have 20 is equal to 180 over x. All right, when I solve this, I want to get x by itself. Right now it's in the denominator, and that's hard to deal with. So I'm going to multiply that denominator so I get rid of the fraction. So now I have 20x equals 180, because remember, when you multiply by a denominator, it crosses out or makes 1. Well, if I want to get x by itself now, I'm going to divide by 20, because it's being multiplied by 20 right now. So I have x is equal to 180 divided by 20 is 9. So I have 9 people.
Is Mr. Lynch isn't here?